Okay, so we're now going to talk about a really famous result, and I think one of my, I think one of the nicest results in all of maths, to be honest. This is called Cauchy's integral formula. Um, so let me write that down. Cauchy's integral. Okay, so what does this result say? So the idea is, let's say you have a closed contour C. So let's say you have some random closed contour. So something like this, let's say, being traversed in the anti-clockwise direction. That's very important. And let's say you have some point Z0, which is interior to C. So it doesn't lie on the boundary, it's strictly inside C. So let's say somewhere here. So let's say you have that. And on top of that, you have a function that's analytic uh, inside and on the boundary of C. So suppose you have a function f and it's analytic inside and on a closed contour C. So closed contour means it's just a loop like what I've drawn here. In that case, we have the following result. Cauchy's integral formula says f of z0 is given by the following formula. 1 over 2 pi I integral around c of f of z0 z minus z0 dz. So why do I like this result so much? Well, there's a lot of results in mathematics like this where they say that the value of a function at a point is somehow given, that's somehow related to the value of the functions along the boundary. And that's exactly what this is saying. You have some point z0, which is inside C, and it just so happens that the value of f at z0 is given by the integral of f around the boundary. And I think that's quite remarkable how that's even true. But that's what the result says. And using this, you can calculate a lot of really nice integrals. So I'll start out with an easy example and then I'll gradually build the difficulty. So first let's have a look at this one here. So I want to evaluate the integral along C of e to the z, z minus 3 dz, where C is the circle. I'm going to take the circle modulus of z equals 4, taken anticlockwise. Okay, so let me just draw what's happening. I have a circle modulus 4. So let's pretend that's a circle. So radius of 4, and it's going anticlockwise. So I want to integrate e to the z on z minus 3 around a circle. How do I do it? I use Cauchy's integral formula. So what I do, the trick is, let f of z to equal e to the z. I'm going to take that to be my function. And remember, in Cauchy's integral formula, you consider a point, what I've called z0, that's interior to C. So I'm going to take that point z0 to be the point z equals 3. I'm going to take that as my interior point. And by doing so, I can use Cauchy's integral formula. So what you write, you say that since f is analytic in C, and not just in C, it has to be analytic in and on C. So in and on C. So how do I know this? Again, because the exponential function we know is entire, meaning it's analytic everywhere. So of course it's going to be analytic within and on the boundary of C. So since f is analytic in and on C, and z equals 3 is interior in C, right? It doesn't lie on the boundary, it's strictly interior. Because those two conditions are satisfied, I can use Cauchy's integral formula. So it follows, it follows by Cauchy's integral formula, which you can write as CIF for short if you like, that. So what does the formula say in this case? F of 3 equals 1 on 2 pi I integral of C around C f of z on z minus 3 dz, right? Now remember, f was the exponential function, so f of 3 is just going to be e cubed okay. So rearranging this integral, we get our answer. So 2e cubed pi I. So that's how you use Cauchy's integral formula. And before I keep going, I should mention I couldn't have, even though I'm integrating around a closed loop, I mean, your instinct may have told you to go with Cauchy's integral theorem, but I couldn't have done that because, remember, if you're going to use Cauchy's integral theorem, you need a simply connected domain which contains C, and that part's not the issue actually. I can easily draw a simply connected domain D which contains C, but the problem is that my function e to the z on z minus 3 is not going to be analytic inside D, right? Because you can't have a denominator of 0, that function is not going to be analytic at 3. And for that reason, I can't use Cauchy's integral theorem, and I have to go with Cauchy's integral formula. Right? Okay, so that was a sort of easy example to get us started. Let's just do another example. So what about this one here? So evaluate integral of cos z on z dz, where C is the unit circle, going anticlockwise. So I guess this one is a little bit trickier than the previous one. because it's not so obvious how to apply Cauchy's integral formula. So, because remember, what does Cauchy's integral formula say? It says that f of z naught is equal to 1 on 2 pi I integral along c f of z z minus z naught dz. So in the previous example, it was sort of clear that I can use Cauchy's integral formula because my function sort of resembled this formula here. I had z minus 3 on the denominator, and the formula has z minus z naught on the denominator. So sort of a given, I can take z naught to equal 3. Not so clear here what to do. But, in fact, let me draw what's happening first. So I have the complex plane, I have the unit circle, so this is 1, and I'm going in the anti-clockwise direction, and I need to use some point which is interior to the unit circle. And the idea in this case is you have cos z on z, so the denominator is just z, but what you can do, you can think of the denominator as being z minus 0, and then use 0 as your interior point. So that's the trick with this question. So take your interior point to just be 0, and then go from there. So if I let f of z to equal cos z, right, I can say since f is analytic inside and on C. Again, how do I know this? Because cos z is an entire function, so it's going to be analytic in any part of the complex plane. So since f is analytic inside and on C, and z equals 0 is interior in C, I can use Cauchy's integral formula. So by Cauchy's integral formula, I have f of 0 equals 1 over 2 pi I f of z z minus 0 dz. Right? And then it's just a matter of rearranging. So you have cos of 0, it's 1 on 2 pi I, cos z on z dz. So therefore, the integral they've given us is just 2 pi I times cos of 0. Cos of 0 is of course 1. So you get an answer of 2 pi I. And that's how you do that example there. Okay. Let's do another example just to get the hang of this. So now I'm going to evaluate integral along C of sine of pi z over z minus I dz, where C will be the circle of radius 2. So taken anti-clockwise. Okay, so let's draw what's happening there. Alright, so you have circle of radius 2 being traversed in the anti-clockwise direction, and because you have a z minus I on the denominator, that's an indication to take the point I to be your interior point, and I is going to be somewhere there, right? So, similar to the previous example, I let f of z to equal sine of pi z. And again, sine function is entire, so of course it's going to be analytic inside and on C. So since f is analytic inside and on C, and because z equals I is an interior point, and z equals I is interior to C, then I can use Cauchy's integral formula. Which I'll write as CIF for short. That's f of I is going to equal 1 on 2 pi I. So let's see, it's going to be f of z minus I dz. So just a straight application of the formula. So again, f was sine pi z, so f of I will be sine of pi I. So you get this. And now you rearrange to get your answer. So therefore, this integral is going to equal 2 pi I times sine of pi I. How do you evaluate sine of pi I? You got to use the definition. So remember, what was the definition of sine of z? Sine of z was equal to e to the iz minus e to the negative iz on 2i. So if I use that definition there, I'm going to get, let's have a look. Pi I times I is going to be negative pi, and negative I multiplied by pi I will give positive pi all over 2i. So now the 2i is going to cancel actually, so I'm just going to be left with this. And that's my answer. So, those examples were just to give you a bit of a feel for how to apply this formula. Now let's look at a slightly harder example. Okay, so let's have a look at this one here. So now what I want to do, I want to evaluate this integral. Z plus 2i. So that integral here, a bit messier than the previous ones. And I'm going to take C to be the circle of radius 3. So C is modulus of z equals 3 taken anticlockwise. Okay, so what's happening here? Got circle of radius 3, and you're going in the anti-clockwise direction. So how does one do this integral? Well, if you have a look at that function that we're trying to integrate, that fraction z over 25 minus z squared, z plus 2i. If you think about it, where is that function not going to be analytic? It's only, well, it's going to be analytic everywhere except for when the denominator equals 0, because you know you can't divide by 0. And when does the denominator equal 0? Well, one possibility is when z equals negative 2i, which will fall inside C. And the other two places where the denominator will be 0 is when 25 minus z squared equals 0. Or in other words, when z equals plus or minus 5. But those points, as you can see, are going to lie outside the circle. So in other words, what I'm trying to say is that function which we're integrating, it's analytic everywhere except for the 3 points that I've drawn. And out of those 3 points, it's only negative 2i that lies inside C. So I should label that. So the trick in this case is to actually take your function to be this. Right? Then as you can see, this function, because 5 and negative 5 lie outside of C, that function f there is going to be analytic inside and on C. So I can say since f of z is analytic inside and on C, and I'm going to take my interior point to be negative 2i. And z equals negative 2i is interior to C. So I have both conditions satisfied, and I can use Cauchy's integral formula. It follows from Cauchy's integral formula that f of negative 2i equals 1 on 2 pi I c f of z minus 2i dz. Right? That's what Cauchy's integral formula says. Now if I plug in what do I know, f of negative 2i is going to be negative 2i on 25 minus 2i squared. What am I going to get on the right? Well, f of z is this fraction. And you want to divide that fraction by z plus 2i, because a negative makes a positive. Okay. So on the left, if I simplify the left, I get negative 2i on 25 minus, well, it's going to be 4i squared, isn't it? Which is going to be negative 4. And if I divide these two fractions on the right, I'll just get the integral I started with. right? And now I can just rearrange and simplify to get my answer. So therefore, that integral which they gave me, it's going to equal 2 pi I times what I have on the left here, which is negative 2I on 29. Okay, so I'm going to get, well, I times minus I is negative I squared, which is negative of negative 1, which is positive. So I'm just left with 4 pi on 29. So that one's a little bit of a trickier example. Although, as you can see, it wasn't that hard because there was a systematic way to it. We just looked at the function they gave us, and we just tried to distinguish between. We tried to figure out at which points is our function not analytic, but which of those points actually lie inside the contour, and we went from there. Okay, I'll do one more example, and this one I guess is a little bit harder, but still not that hard. In any case, I don't think it'll get any more challenging than this one. So let's have a look. I want to evaluate the following integral. Sine pi z plus cos pi z on z squared minus 3z plus 2 dz, and I'm going to take C to be the circle of radius 3. Taken anticlockwise. Okay. Now, what is the trick with this question? The trick with this question is to firstly factorize the denominator and then use partial fractions. By doing partial fractions, you're going to split the integral into two separate integrals, and then you can use Cauchy's integral formula on each integral. So I'll show you what I mean. So firstly, note 1 on z squared minus 3z plus 2. Okay, if you factorize that quadratic, you're going to get z minus 2, z minus 1. And now what I want to do, I want to split this using partial fractions. So remember, how do you do this? You write it as some letter, let's say capital A, on z minus 2, plus let's say capital B on z minus 1. Whoops. Like that. And I want to find the A and the B to make this split valid. Okay, how do you do this? Well, you literally go ahead and you add the fraction on the right. So if you add these two fractions together, you'll get A z minus 1 plus B z minus 2 all over z minus 2 z minus 1, right? And you can see that the denominator of this fraction is equal to the denominator of this fraction, right? So logically, in order for both fractions to be equal, their denominators should be equal. Sorry, their numerators should be equal as well. So this implies that 1 should equal this. So I get down to there, and how do you figure out A and B? You could expand the right and then equate coefficients with the left. Alternatively, you can just sub in convenient values for z. So if I sub z equals 1 into that equation, on the left I obviously just have 1, but on the right I'm going to be left with a times 1 minus 1, which is 0, plus b times negative 1. So I get 1 equals negative b, or in other words, b equals negative 1. And if I substitute z equals 2, then I'm going to get 1 equals a, or in other words, a equals 1. So that's how you would split it into partial fractions. So what I found that therefore that fraction there this one is equal to 1 on z minus 2 minus 1 on z minus 1, right? And therefore, that initial integral which they gave me, so this one right here, this one can be written as follows. So this one over z minus 2 dz minus same thing over z minus 1. Like that. And now what I'm going to do, I'm going to call this integral here, maybe I'll call it I1, and I'll call this other one I2. And I can compute I1 and I2 separately, and I can compute each of them using Cauchy's integral formula. So for both cases, I am going to let f of z to equal sine pi on z plus cos pi on z, right? In the case of I1, let's think about what's happening. I'm integrating around the circle z equals 3. And as you can see, I have a denominator z minus 2. So to me, that's an indication to take z equals 2 to be my interior point. Right? Now, f is sine pi on z plus cos pi on z. Like I said before, sine and cos are entire, so they're going to be analytic everywhere. And of course, that means their sum is going to be analytic everywhere. So since f is analytic inside and on C, and Z equals 2 is interior to C. We can apply Cauchy's integral formula. So it follows by Cauchy's integral formula that, let's have a look, f of 2 will be 1 over 2 pi I times exactly what I've called I1, right? So therefore I1 will equal 2 pi I times f of 2. That equals 2 pi I times, it's going to be cos 2 pi plus sine 2 pi. Or I should have written sine 2 pi plus cos 2 pi. But anyway, that's just going to equal 2 pi I times 1, which is 2 pi I. Right? So that's the value of I1. Now for I2, you can see that my denominator is z minus 1. So that's an indication I should take the point z equals 1 as my interior point. Right? So then I use exactly the same argument. I say, since f is analytic inside and on C, and z equals 1 is interior to C, I can again use Cauchy's integral formula. So it follows by Cauchy's integral formula that f of 1 will equal 1 on 2 pi I times that integral which I've called I2. So therefore I2 will equal 2 pi I times f1. Now f of 1 is going to be sine pi plus cos pi. Sine pi is 0, but cos pi is negative 1. So this is negative 2 pi I. Right? So now that I know what I1 is and I know what I2 is, I can just put this all together to get my my integral. So therefore, that initial integral which they gave us so this one here. Remember this was, we said this was I1 minus I2. I1 was 2 pi I, I2 was negative 2 pi I, so that leaves me with a final answer of 4 pi I. And that's pretty much how you do it. As you can see, Cauchy's integral formula, it's just a formula that you apply really. It's not really that tricky either. In any case, I don't think you can really get a question trickier than this one. Now, there is another way you could answer this question. You can also answer this question using what was it called? Cauchy's integral theorem for multiply connected domains. So let me show you an alternative solution. Okay, so actually first I need to draw what's happening. So remember, we were integrating around z equals the modulus of z equals 3. So around a circle of radius 3. Okay, so let's say this is 3, and we're going around in a circle. And what was the function we were integrating? We were integrating this one here. So I'll write it out again. So I'll write it in factorized form. So that was the function we were integrating just then. So what do you notice about that function? It's going to be analytic everywhere except for when the denominator is equal to 0. So in other words, it's going to be analytic everywhere except for the points z equals 1 and z equals 2. So let's say those 2 points. Now, the trick, or the alternative trick for this question, is to construct a multiply connected domain. So what you do, you draw circles around 1 and 2. So actually, okay, let's say those are circles. Anyway, I'll call this one C1 and I'll call this one C2. Then you can see if I consider this domain here, right? I have a multiply connected domain. I have a domain with holes, basically. I'll call it D, right? Its outer boundary is C, but its inner boundary is C1 and C2. And, moreover, you can see that that function which I'm trying to integrate, it's going to be analytic within D, isn't it? Because it's avoiding the points z1 and z2. Sorry, the points 1 and 2. So here, what I'm going to say, let D be the multiply connected region above. Right? And like I said, you want to draw C1 and C2 in a way that they, like I've done here, so that they stay within C. So maybe I'll let the radius for each one to be like a quarter, for example. So where C1, C2 are circles of radius a quarter, centered at 1 and 2 respectively. Right? Then in that case, we can see that D is a multiply connected domain, and my function is analytic in that domain. So let me write that down. D is multiply connected. And the function is analytic in D. And so what that means is that we can apply Cauchy's integral theorem for multiply connected domains. So Cauchy's integral theorem for multiply connected domains. Right? Now what does that theorem tell us? Remember, it tells us that then this integral that I have here, it's equal to the integral over c1 of that function plus the integral over c2 of that function. Right? That's what Cauchy's integral theorem for multiply connected domains tells us. And now each of those integrals, I'm going to treat them separately. So I'm going to call this one I1, and I'm going to call this one I2. I can compute I1 and I2 separately using Cauchy's integral formula. So in the case of I1, what I can say is let f1 of z to be equal to this function. Z minus 2. Right? Now, can you see that f1 is going to be analytic inside c1, right? Because the only place where f1 is not analytic is when z equals 2. And the way you can see I've drawn my diagram, c1 avoids z equals 2. So what I can say then f1 is analytic inside and on c1, and obviously z equals 1 is interior to c1, it's its center. So therefore I can apply Cauchy's integral formula. So it follows by Cauchy's integral formula that what we have is f1 of 1 is going to be 1 over 2 pi I times that integral, which we've called I1. So I1 will be 2 pi I times f1 of 1. Now, what is f1 of 1? It's going to be sine pi plus cos pi over z minus 2, so negative 1. Sine pi is 0, cos pi is negative 1, so we'll cancel with the negative 1 on the denominator. You're just going to be left with 2 pi I, like that. And then I do a similar thing to calculate I2. So for I2, what you do is you let f2 of z to equal the same function, but now we're going to take the denominator to be z minus 1. And the idea here is that now F2 is going to be analytic in C2. And moreover, Z equals 2 is going to be interior in C2, right? Again, it's just its center. Okay, so again, I can apply Cauchy's integral formula. Which tells me that f2 of 2 equals 1 on 2 pi I times I2. Right? So therefore, I2 will equal 2 pi I times f2 of 2. So that's 2 pi I times sine 2 pi plus cos 2 pi over, so it's going to be over 2 minus 1, which is 1. Now sine 2 pi is going to be 0, cos 2 pi is 1, so this gives me 2 pi I as well. Right. Now putting it all back together, remember my integral was I1 plus I2. So therefore, that initial integral which they gave us, it's going to be I1 plus I2, so it's going to be I1 plus I2, which equals 2 pi I plus 2 pi I, which is 4 pi I. So you can see we got exactly the same answer we got before. So this is an alternative method for computing the same integral. The advantage of this one is you can avoid doing partial fractions, and also you get to use Cauchy's integral theorem for multiply connected domains, which is a very cool thing to use. Okay, that's pretty much it.